Have you ever wondered how plant-derived products are separated for analysis and identification? Chromatography, a sophisticated scientific technique, is the unsung hero behind this process. It plays a pivotal role in the separation and identification of different components within a mixture. The world of plant-derived compounds is incredibly diverse, containing everything from essential oils to medicinal components, and chromatography helps us make sense of this complexity. It allows us to isolate, identify, and analyze these components, opening up a world of possibilities for research and application. From developing new fragrances to discovering novel therapeutic agents, the applications are as diverse as the compounds themselves. But how does chromatography achieve this? Well, there's more than one way to separate a mixture. In this video, we'll delve into 5 chromatographic separation techniques and their applications in the analysis of plant-derived products. Let's start with a simple yet effective technique: paper chromatography. In the vast world of chromatographic separation techniques, paper chromatography stands as a pillar of simplicity and efficacy. So, what makes it tick? The principle behind paper chromatography lies in the separation of components based on their relative affinities towards the stationary phase, the paper, and the mobile phase, a solvent. In other words, it's a tug of war, with each component in the mixture being pulled between the stationary and mobile phases. Imagine a marathon where each runner, representing a component in the mixture, has a different speed. The stationary phase, our paper, is the marathon track, while the mobile phase, our solvent, is the force propelling the runners forward. As the solvent seeps up the paper, it carries the components of the mixture along with it. Each component travels at its own pace, separating from the others based on its own unique affinity for the stationary and mobile phases. Now let's talk about the process. We start by marking the origin, a point near the bottom of our paper strip where the sample is applied. The strip is then placed in a solvent, ensuring the origin remains above the solvent level. As the solvent rises through capillary action, it carries the sample components upwards, each at a different rate, resulting in a series of spots at different heights. This is the resulting chromatogram, a visual representation of our separated components. So, where does paper chromatography shine? Its simplicity and cost-effectiveness make it a go-to method in many fields, including the study of plant-derived products. It provides a reliable way to separate complex mixtures in plant extracts, helping us identify and quantify various components like pigments, alkaloids, and flavonoids. It's a key player in fields like phytochemistry, where it aids in the identification and analysis of plant metabolites. Paper chromatography, though simple, provides a reliable method for separating complex mixtures in plant extracts. So, next time you think of separation, remember the marathon of paper chromatography. Moving on to another widely used technique, thin layer chromatography, or TLC. Now, what makes TLC so special? It's a simple yet powerful method for separating mixtures, and it's particularly effective in the analysis of plant-derived compounds. Imagine TLC as a race, where different compounds are the runners and the finish line is the top of the plate. Each compound races up the plate at a different speed, depending on its affinity for the stationary phase, the thin layer of silica gel on the plate, and the mobile phase, the solvent in which the plate is dipped. This difference in speed separates the compounds, allowing us to analyze them individually. The principle behind TLC is quite straightforward. It's all about the balance between the stationary and mobile phases. A compound that has a higher affinity for the stationary phase will move slower, while one with a higher affinity for the mobile phase will move faster. This is called partitioning, and it's the heart of TLC. So, how does this apply to plant compounds? Well, plant extracts can be complex mixtures of various compounds. With TLC, we can separate these compounds and identify them based on their unique properties. For example, we could separate the various pigments in a leaf extract and identify them based on their color and the distance they traveled on the plate. But it's not only about identifying compounds. TLC can also help us quantify them, determine their purity, and even monitor the progress of a reaction. And the best part? It's all done on a small, portable plate, making TLC not just effective, but also highly convenient. Even in the era of more advanced techniques, TLC holds its ground. It's quick, it's simple, and it's efficient. It doesn't require large sample volumes or expensive equipment, making it accessible to labs of all sizes. TLC, with its ease of use and efficiency, remains a popular choice in the analysis of plant compounds. And that's the beauty of it. It's a testament to the timeless principle that sometimes simplicity is the ultimate sophistication. Now, let's turn to more advanced techniques: high-performance liquid chromatography and high-performance thin-layer chromatography. High-performance liquid chromatography, or HPLC, is a highly sophisticated technique that uses high pressure to propel a liquid solvent containing the sample mixture through a column filled with a solid adsorbent material. Each component in the sample interacts slightly differently with the adsorbent material, causing different flow rates for the different components and leading to the separation of the components as they flow out of the column. HPLC has been widely used in the separation and analysis of plant-derived compounds due to its high resolution, sensitivity, and speed. It enables the identification and quantification of individual compounds in complex plant extracts, helping researchers to understand the chemical composition and potential therapeutic benefits of these natural products. On the other hand, high-performance thin-layer chromatography, or HPTLC, is a refinement of thin-layer chromatography. It involves the separation of compounds on a thin layer of adsorbent material, typically silica gel, coated onto a flat, inert carrier material. In HPTLC, the sample is applied to the plate in a small spot and developed in a suitable solvent system. The separated compounds can then be visualized and quantified. This technique offers several advantages over traditional TLC, including greater sensitivity, better resolution, and the ability to analyze multiple samples simultaneously. Like HPLC, HPTLC is a powerful tool in the analysis of plant-derived compounds. It is particularly useful in the quality control of herbal medicines, where it can be used to verify the identity and purity of the herbal ingredients. In conclusion, HPLC and HPTLC, with their high resolution and sensitivity, are indispensable in the modern analysis of plant-derived compounds. These advanced chromatographic techniques provide valuable insights into the complex world of plant chemistry, aiding in the discovery and development of new drugs and therapies from nature's medicine cabinet. HPLC and HPTLC, with their high resolution and sensitivity, are indispensable in the modern analysis of plant-derived compounds. Last but not least, let's explore column chromatography. A powerful tool in the scientist's arsenal, it's leveraged in labs worldwide for its simplicity and effectiveness. Imagine a tall column packed with a stationary phase, often a finely ground solid, or a liquid on an inert solid support. This column serves as the battleground where separation occurs. The mixture to be separated is loaded onto the top of the column, followed by more solvent, known as the eluent. The eluent carries the mixture through the column, and here's where the magic happens. Each component in the mixture interacts differently with the stationary phase. Some compounds will bind more strongly and move slowly, while others will bind less and move faster. This difference in travel speed enables the separation of components. The separated components, now termed eluates, are collected at the bottom of the column. The principle behind this dance is one of equilibrium. It's a constant back and forth of compounds binding to and being released from the stationary phase, with the balance of this equilibrium determining who races ahead and who lags behind. Now, how does this play out in the world of plant-derived products? Well, column chromatography shines here. It is widely used to separate and purify individual components from complex plant extracts. Each plant-derived compound, be it a pigment, a flavoring agent, or a potential new drug, has its unique interaction with the column's stationary phase. By tweaking the column conditions, scientists can isolate their compound of interest from the rest of the plant extract. So, whether it's the vibrant colors in a flower petal or the potent compounds in medicinal plants, Column chromatography has a hand in revealing them. It's an elegant dance of chemistry, where the stationary phase and the eluent set the stage, and the plant compounds take the spotlight. Column chromatography, with its versatility, has wide applications in the separation and purification of plant compounds. We've covered a lot of ground in understanding the role of chromatography in the analysis of plant-derived products. Let's take a moment to recap. We started with paper chromatography, a simple yet powerful technique for separating mixtures into their individual components. We then moved on to thin layer chromatography, a method that gives us a quick and inexpensive way to monitor the progress of chemical reactions. Next, we delved into high-performance liquid chromatography and high-performance thin layer chromatography, techniques that offer high resolution and sensitivity, making them ideal for complex analyses. Lastly, we explored column chromatography, a technique that excels in separating compounds from large, complex mixtures. Each of these techniques has its unique strengths, and their applications in analyzing plant-derived products are vast and varied. They provide us with an in-depth understanding of the complex world of plant compounds. So subscribe for more, because you won't find me later. Stay curious, keep exploring, and continue expanding your knowledge with us.